logarithms and logarithmic functions. So first of all, what is a logarithm? So we know that 2 squared is equal to 4 and 2 to the third equals 8. But what is x to make 2 to the x equal to 6? Well, we define this value as using a logarithm. So we can kind of think of logs as being inverses for exponentials. Just like square roots and squares are both inverses of each other. So here's how a logarithm looks. So log base b of y, that's how we read that. Log base b of y is equal to x, if and only if b to the x is equal to y. So these two statements are related. So this is the log format, and this is the exponential format. So here's how you can convert between the two. So it's going to be b to the x power is equal to y. So see, b to the x equals to y. So let's talk about converting from one to the other. So log base 2 of 16 is equal to a 4. This is a true statement, so we're not worried about whether or not this is true. We're just trying to convert from log form to exponential form. So right now this is in log form. So 2 is your base. Now a base is basically what number set are you in. So it's going to be 2 to the fourth is equal to 16. This is the exponential form, and you can check this yourself. 2 to the fourth does in fact equal 16. Now example 2, log base e of 1 is equal to 0. So again, e is your base. This is that natural base e that we talked about earlier. E to the 0 power is equal to 1. And again, you can check this as well. Anything to the 0 does in fact equal 1, so this is true. Log base 12 of 12 is equal to 1. So again, 12 is your base, start there. So 12 to the first is equal to 12. Check if that's true. 12 to the first, well, that is just 12, so we're good. Now there's a fraction in the base, that is okay. So we have the base as being a fourth, so this is your b, 1/4 to the negative 1 power. When we write this, we need to make sure we put that base in parentheses this time, because there's more than just a single number in there. So 1/4 to the negative first power is equal to 4. That's converting from log form to exponential form. Now let's go the other way. For each of the examples below, rewrite in log form. So again, 5 squared does equal 25. We're not worried about if it's true or not. We're just trying to write this in a different format. So remember, this was your base. So we're going to have log base of 5 of 25 is equal to the exponent, 2. Log base 5 of 25 is equal to 2. It's always going across the equal sign first and then backwards. So 10 is your base, so it's going to be log base 10 of 0.1, you can use parentheses or not, it's up to you, is equal to negative 1. 8 is the base, so it's going to be log base 8 of 4 is equal to 2/3. So 8 to the 2/3 power equals 4. Then 6 is your base, 6 to the negative 1/3 power, so b. So log base 6 of 1/216 is equal to negative 3. That's changing backwards into log form. So now let's talk about evaluating these logarithmic expressions. So evaluate each logarithmic expression below. So I'm basically trying to figure out the number that this is going to equal. So log base 4 of 64, what does that equal? I don't know about you, but I think better in exponentials. Logs are very abstract for most people. So I'm going to make this into a little equation. Since I don't know what this equals, I'm going to put an x there. Now that I have a little equation, I'm going to change this into its exponential form. So that means 4 is your base, So 4 to the x is equal to 64. This is a little bit easier to think about intuitively. So we're trying to figure out 4 to what power will give me a 64. Well, I can do some either mental math or I can do it to the side. So 4 times 4, this is to the second power, that's 16. If I multiply 4 again, that's to the third power. 16 times 4 makes 64. So that means that x must be equal to a 3. So log base 4 of 64 is equal to 3. Example 10, log base 5 of 0.2. Again, I'm going to change this into a little equation. Since I don't know what this is equal to, I'm going to put it equal to x. Change this into exponential. So take your base, that's a 5. So b to the x power, 5 to the x, is equal to 0.2. Now, decimals are also not my strong suit. Well, 0.2 as a decimal is 1/5. This is a little bit easier. So if I notice, the 5 is still a 5. One thing that happened was instead of being on the top of a fraction, it switched down to the bottom. So what exponent is not going to change my number, but is going to flip my fraction? Well, that has to be a -1. That's what negative exponents do. If you do 5 to the negative first, that means that this is going to drop to the bottom, it become positive, and put a 1 on top. And well, 1 over 5 to the first is just 1 over 5. So this is kind of playing with your exponent rules as well. Log base 1/5 of 125. Again, I don't know what this is, so I'm going to put equal to x. So here's my base. So 1/5 to the x is equal to 125. So again, I got to worry about fractions here. So 1/5 to the x somehow has to get me to 125. Well, if you notice, 125 is not a fraction. So that means I have to get this 1/5 out of the fraction. So that automatically means my x has to be a negative number. That's the only way to flip-flop the fractions when you have exponents. Now 5 to the what power is going to give me 125. So I'm going to start doing some either mental math or actual calculations. 5 times 5 gives me 25, so that's the second power. If I multiply by 5 again, I get 125. So that's what I needed. So the power is going to be a 3. So the negative is what flipped the fraction, got my 5 out of the denominator. Then the 3 is what gave me 125. Log base 36 of 6. Don't know what this is, so make it a little equation equal to something. So it's an x. So 36 to the x has to be equal to 6. So 36 to the what power is going to give me a 6. So this is exponents here. We're not dividing. We're raising something to a power. I need to get from a large number to a small number. Now, if you noticed, whole numbers in the exponent make my numbers larger. So if I raise something to a 3, I get a bigger number. Even on example 11, 3 gave me a larger number. I need to get to a smaller number, so I need something that is less than 1. Well, I do know that the square root of 36 is equal to 6, but how do I write a square root as a exponent? Well, square roots are just halves as exponents. So that means x has to be 1/2. If I needed a cube root, it would have been 1/3. If I needed a fourth root, it would have been 1/4. Now, there's two special types of logs. So we have a common logarithm. That is a log with a base of 10. So log base 10 of x, we don't actually write the 10 as the base. We simply just write log of x. That's it. And the reason why it's assumed to be a 10 if no base is shown is because that's how our numbers work. We work in a number system of base 10. From 0 to 9, there's our 10 numbers. Computers work in a number of base 2, zeros and ones. Time is in base 60 because there's 60 seconds in a minute. So there's different bases depending on what numbers you're working with. We primarily work in base 10, which is why we don't put the base 10 if it's assumed to be there. Another base that we write is we write the natural log. So this is a log with base e. That's that 2.17 number we talked about earlier. Now, a log with base e, we actually change the notation a little bit. We do ln of x. That's called the natural log. This always has a base of e. So if you see ln of a number, you know its base is an e. If you see a log without a base, we assume the base is 10. Graphing logarithmic functions. So let's talk about the parent function for logs for just a minute. So we have two pictures here. Now if you notice, there's two graphs on this, so you have to pay attention to what we're talking about. So this blue one is actually b to the x. That's your exponential, as long as b is greater than 1, so that means it would be exponential growth. Log base b is this red function here. Now, we do have asymptotes for a logarithmic function as well. So exponentials had an asymptote at y equals 0 here on the x-axis. Well, logarithms have an asymptote there vertical at the line x equals 0. So exponentials have a horizontal asymptote, logarithms have a vertical asymptote. Then we have another graph for exponential decay, essentially. So b is less than 1 but bigger than 0, so a fractional base. And this is what the log function will look like then. Again, you still have a vertical asymptote at x equals 0. So the functions log base b of x and b to the x are inverses. So that means two things. That means they are reflections over the line y equals x. It also means that their domains and ranges are inverted. So let's talk about how to graph one of these. So here's your basic steps. We're going to go through these piece by piece. So step 1 is find the exponential form of the logarithm. Basically, its inverse. So example 1, graph f of x equals log base 2 of x, and then identify the domain and range. So to graph these, it is easier to graph when we're talking about exponential functions instead of logs. Exponentials come a little bit easier. So remember that f of x is just fancy for y. So if I try to change this to its exponential form, 2 is my base. So it's 2 to the y power is equal to x. But again, since it's an inverse, we always invert the x and the y variable. So we actually have 2 to the x is equal to y. Or, if it looks a little nicer, y equals 2 to the x. Now, step 2 is make a table of values for the function found in step 1. So we're going to make a table for this exponential function. So I'm going to start with like -2, -1, 0, 1, and 2. That should be enough to get us an idea of what's happening. So if I substitute -2 in for x here, we're going to get a value. So 2 to the -2 power is 0.25. 2 to the -1st power is 0.5. 2 to the 0 is a 1. 2 to the 1st is 2. And 2 squared is 4. Now, this is not the function you wanted to graph. Keep in mind, this is that exponential function. So, step 3 would be used if you wanted to plot the exponential function. So if it asked you to graph the log and its inverse, we would use step 3. But in this case, we just want the log. So we're not going to plot these points just yet. So we're going to move on to step 4. Use the property of inverses to get the other table. Well, the property of inverses means you're going to invert the x's and the y's. So I'm going to make a new table for my log function. Now, the x of my exponential is actually the y of my log. So all of my y values will be -2, -1, 0, 1, 2. Then the y's for my exponential are actually the x's of my log. That's what inverses do. They interchange the x and the y. So the x's for my logarithm is 0.25, 0.5, 1, 2, and 4. Now we have the table for my logarithmic function. So now we can go ahead and start graphing my log. So we have the x value of 0.25, so that's about here, give or take, and it'll be at a -2 on the y value. Then I have half, and that'll be at -1, 0, 1, 2, 1, and 4, 2. Now remember, this has a vertical asymptote here at x equals 0, which is why these numbers down here were getting really hard to graph because they're getting closer and closer to that vertical asymptote. So it makes sense numerically. So if we connect this line with a smooth curve, there's my graph. So this blue dashed line, that's your vertical asymptote at x equals 0. Now the domain and range for this. So domain, we're used to having as all real numbers most of the time. Well, since I have a vertical asymptote at 0, it's no longer all real numbers because I'm not allowed to go into my negative x's. So the furthest left I'm allowed to go is 0, but because of this asymptote, I'm not allowed to actually hit 0. Then the highest I'm allowed to go, well, this goes to the right forever, so that's infinity. So you could also write this in the inequality as x greater than 0. Now range is usually where we have the restrictions, like stopping at 5 or stopping at -2. But let's look at this graph. This arrow points down forever, and this one is also going up forever. So the furthest bottom my graph will go is -infinity, but the highest it goes is also infinity. So range for this case is all real numbers. And that's that fancy little R symbol.